I'm very sorry not to be with you today. I hope this recording is a reasonable stand-in. I'm going to talk about the problem of selecting the best simulated system when the number of feasible solutions is large, but the parallel computing capacity is also large, so we're going to simulate them all. This is joint work with my PhD student Linda Pei and Susan Hunter from Purdue. A little bit of background on ranking and selection. Generically, we'll say that there are k alternatives, and their means are mu1, mu2 through mu_k. And unknown to us, mu_k is the best system. So in fact, we'll refer to system k, or any system tied with system k, as being the best. For each system, we don't know its true mean, but we can estimate it with a consistent estimator such as the sample mean from n sub I replications. So I'll call sample means y bars throughout the talk, and if I need to indicate the number of observations, n sub I in parentheses. And then most ranking and selection procedures, whatever they do in the middle, in the end will pick the system with the largest sample performance measure. So in this case, capital K hat is the system with the largest sample mean, since we're trying to maximize. There are a wide variety of ranking and selection procedures, but many of them have as a basic building block looking at certain standardized pairs of differences. So the part of the formula highlighted in blue is the difference between the sample mean of system K, which is in reality the best system, and some other system I, with a standardization based on their variances in the number of observations. And when the outputs of the simulation are normally distributed, this standardized sum of differences can be approximated as a Brownian motion process with a drift, where the drift is based on the difference between the true means. Now the reason this is done is because a lot is known about Brownian motion with drift crossing certain boundaries. You can see an example at the right with a triangular region. So this process should have positive drift, meaning it should drift generally upward and cross the upper boundary, and if it does, then system I would be eliminated while system K would be retained. On the other hand, if a mistake is made and it drifts out through the lower boundary, then system K would mistakenly be eliminated while system I would survive. Using this kind of approach, many classical ranking and selection procedures work like the algorithm shown below. Until one system is remaining, generate a single replication from all currently surviving systems. Do a pairwise comparisons like what's shown above, eliminate any systems that cross some important boundary, and continue until just one system remains. And the typical sort of guarantee that one gets is something like the probability of correct selection being greater than or equal to 1 minus alpha, where probability of correct selection here is defined as the probability that the system you select, system K hat, the probability that it equals the best system is greater than or equal to 1 minus alpha, provided the gap between the best and the second best is at least delta, another user-specified parameter. Now notice that there's a lot of coordination in this process. A single replication followed by pairwise comparisons. A single replication followed by pairwise comparisons. We want to create procedures that are specifically designed for very large numbers of alternatives. The example I'll show you at the end has 22,500 simulated alternatives, and also exploits parallel computing capacity. So the first thing we want to do is to look for error control that is more scalable than probability of correct selection, yet is still useful and understandable. PCS is a family-wise statement, and as a result tends to become more and more difficult to attain the larger the number of systems are. So we'll introduce the idea of expected false elimination rate of systems that we consider to be good. Now, generically, we consider a system to be good if its mean is greater than or equal to some standard that we call mu star. In this talk, mu star will be the value of the mean of the best system, because that's the setting that's closest to standard ranking selection. We're also looking for procedures that get better when the number of systems K and the number of parallel processors P are large. In fact, the procedure I'm going to show you at the end is a really poor choice when K is small and there's only one processor. To do this, we want to avoid coupled operations and synchronization, like the procedure I just showed you, and we want to exploit averages over large numbers of systems. Not averages over large numbers of observations from each system, but averages over large numbers of systems. This will come together in an algorithm that we call BiPASS, which is bisection, parallel, adaptive survivor selection. To be able to describe our new approach, we also need a new framework. Now, ultimately, we'll be looking at the cumulative sum of observations, say, from system I. That is a discrete time process. But to develop our approach, we'll work with a corresponding continuous time process, B sub I of t, which represents the cumulative amount of data collected on system I by time t. And that will be a standard zero-drift Brownian motion process, Wi of t, plus t times mu sub I, where mu sub I is the mean of system I. Because we're going to be simulating things in parallel, where the number of systems K will typically be much larger than the number of worker processors P, we're going to distinguish between local time for system I, which is the cumulative amount of data collected on system I, and the global or computer or clock on the wall time tau. Now, these things are connected by the function we call R sub I of tau, which is just an indicator function that's 1 when system I is running on one of the worker processors at time tau, and is 0 otherwise. Therefore, the local time, that is the cumulative amount of data that's been collected on system I, by global or computer time tau, is given by the expression at the bottom of the slide. T sub I of tau is the integral from 0 to tau of the indicator function times beta sub I. Now, beta I represents the rate at which we accumulate data or advance local time as a function of the global time tau. And we'd typically expect beta I to be much greater than 1 because we simulate much faster than real time. This figure illustrates the difference between local time and global time. So on the vertical axis is local time, or the amount of accumulated data for system I, whereas the horizontal axis is computer or wall clock time. Now, in this particular sample path, system I is idle at the beginning, and at some point is assigned to a processor, and then accumulates local time at rate beta sub I until a batch of delta local time has been accumulated. It then is back and idle for a while, waiting for its next time to execute. A bit later, it starts executing again, accumulating another delta of local or accumulated observation time at rate beta I, and so on. There are several quantities that are important to us to identify when we try to do proofs about this sort of process. Moving from left to right, we need to consider things like the first point in time at which system I accumulates delta of local time, and also the last point at which it happens. In addition, given any particular point in time in global time tau prime, we need to be able to say how many cycles of or batches of local time have been collected on system I. To create our new procedure, we also need a new building block to replace that pairwise difference. Our building block we're going to call S sub I, which is the cumulative data recorded on system I, B sub I of t, minus t times the standard. In this case, the standard is mu k, the value of the best system. So doing a little algebra, that's the driftless Brownian motion process, W sub I, minus t times the difference between the true mean of system I and the value of the standard. Now, if system I is tied with the best, this is a driftless process. On the other hand, if mu I is inferior, or what we'll say is not one of the good systems, then the drift is negative. We're going to monitor this process using a non-decreasing function g that has the following property. The probability that S sub I, our cumulative sum for system I, ever crosses minus g of t, that is, crosses in the negative direction, for any t less than infinity, is guaranteed to be less than or equal to alpha if system I is tied with the best system, and is guaranteed to be 1 if system I is one of the inferior systems. You can see a picture on the right where the smooth curve is minus g of t, and the cumulative sum processes for two different systems I are shown, one that appears to be one that will never cross the boundary, and one that does cross the boundary and therefore will be eliminated. We let script g be the set of all systems whose means are as good as the best, and we'll call these the good systems. And what we want to do is control the rate at which good systems are eliminated. Now, if I actually knew the value of mu k, that is, the true mean of the best system, and could actually compute the sum as I've shown it here, then clearly the expected false elimination rate of good systems is less than or equal to alpha, just by the properties of the function g, and even better, there's no coordination required. That is, I can run each system individually in whatever way I want without ever having to know anything about the other systems. That'd be great if that was the case, but the problem is more interesting when I don't actually know the value of the standard, and that's what we move to next. Our new procedure is called bypass. The idea of bypass is to learn the standard, in this case mu k, as we go with as little coordination as possible while not compromising the expected false elimination rate. And the idea is really simple. Mu bar of tau, that is the estimated standard at global time tau, is just going to be the average of the sample means of all surviving systems. So here the set script Q is the set of all systems that are still in play, that are for survivors by time tau, and we're summing that over the sample mean of all the outputs collected from those systems. So bypass acts kind of like a bisection search in the sense that the estimated standard is always sort of in the middle of the true means of the systems that have survived. Now, does this compromise the expected false elimination rate? And we show in two regimes that the expected false elimination rate is still preserved at being less than or equal to alpha. We have a stylized setting, the synchronous setting, where the number of worker processors is equal to the number of the systems, and the surviving systems are always in sync. For this, we can get an exact result. When we allow things to be asynchronous, like the picture I showed you earlier, then we can show that bypass preserves the expected false elimination rate as the number of systems goes to infinity, and the ratio of the number of processors to number of systems converges to a constant between 0 and 1, meaning we're guaranteed that we always have enough processors that we can keep up. This picture indicates how bypass works. There's a master processor indicated in purple and P worker processors indicated in green. And the black icons are the jobs or systems. The master has a queue of systems that it assigns to the workers when a worker becomes free. A worker simulates a system for a batch of observations, either eliminating the system, like what's happening with system 88, or if the system survives that batch, returning it to the master, who uses the accumulated data to update mu star, the estimated standard, based only on the survivors. Now the proofs of these results are long and tedious, but I want to give some idea of how they work. First of all, there's the obvious insight that when we actually look at a discrete time process, the expected false elimination rate is less than or equal to what it would be for the continuous time Brownian motion process because there are just fewer chances to make a mistake. The second important insight is that the most difficult case for preserving the expected false elimination rate is when all of the systems are tied with the best. Another insight that plays a big role is that lower variance of the process implies a lower expected false elimination rate when we keep the same boundary, and a smaller survivor set Q leads to a lower variance. We then had two regimes: the synchronous regime, when the number of processors equals the number of workers and systems stay in sync. Why is this hard? Well, because elimination changes the Brownian motion process. The key result here is that, say from the point of view of system K, its partial sum process is independent of the eliminated systems if we recenter the standard immediately after the eliminations. Now in the asynchronous case, which is of course more like reality, why is that proof hard? Well, in the asynchronous case, when systems are running on a worker, their value of the standard is frozen. That is, it can't be updated because they don't see the values from other systems. The key result here is that as k goes to infinity, this frozen standard converges to a constant, and we can show that the expected false elimination rate is preserved. Whenever simulators do comparisons, they always think about common random numbers because comparisons involves differences, and common random numbers tends to reduce the variance of estimated differences. What about for bypass? Well, if I actually knew the value of mu k, that is the standard or the true mean of the best system, then common random numbers would be no help. Each system is compared marginally to the value of mu k. There are no differences, therefore no common random numbers effect. However, the estimated standard, mu bar, contains the sample means of the surviving systems, so there is a common random number effect. Does it help or hurt? Well, the answer to that turns out to be a little complicated. To illustrate it, let's consider a stylized case where, again, the number of processors, P, is the same as the number of systems, K, and the systems are synchronized in the following sense. I send each system that has survived out to the processors to get a batch of delta observations, delta local time. They all come back together, and the standards get updated for the survivors. They have a common variance, 1, so the variance of the Brownian motion process is t, and common random numbers induces a common correlation that I'll call rho. So let's suppose we're at time m delta, that is, we've accumulated m batches of delta local time on each observation, and we're sending system I out to get another batch of delta. What's the variance of SI, the partial sum, as a function of t? That's the expression on the right, and the important quantity is the one that's highlighted in blue. That's t, the current amount of local time we've accumulated, over m delta, which was the amount of local time that was used to compute the standard. Now initially, that's m delta over m delta, or 1. The quantity in parentheses is negative, and therefore common random numbers is going to reduce variance. However, as we continue to run with the frozen standard, t gets bigger, m delta stays fixed, And if we run long enough, then eventually t is large enough, the quantity in parentheses becomes positive, and the variance of the partial sum is increased. So the message is, if we stay frozen too long without updating the standard, then the variance is increased. How long can we stay depends upon how many batches we've already accumulated. But of course, as time goes to infinity, and m delta does as well, eventually we will reduce variance. This is going to be a simple SS inventory problem where the goal is to pick the value of little s and big S, the reorder point and order up to quantity, to minimize the long run average cost. We ran this with P+1 processors, 1 master and 100 workers. We considered a case where there were k equal 22,500 solutions, and we're going to set the desired expected false elimination rate to be 0.02. Now we ran this as a fixed budget procedure, and when the budget was exhausted, BYPASS had 7 systems left that had not been eliminated, including the true best. The plot on the right, when you look at the blue or solid curve, shows the number of surviving system as a function of time in seconds. And so you can see how it falls off very quickly with a few little plateaus, and at the end of this particular run there were 7 systems left. The dotted line is what would have happened if we had run BYPASS with the known standard mu k. For this particular problem, we know the optimal solution, so we can use that. We call that PSS, or parallel survivor selection, and that's the dotted line. So you can certainly see the advantage of obviously knowing the value of the true best, but you can also see that BYPASS parallels that pretty well. Now, one way to think about this result, or at least one way we thought about it, was to do the following. We took the total number of replications that BYPASS was able to execute by the end of this run, then divided that total number equally among all 22,500 systems and ran subset selection. Subset selection is a standard ranking and selection procedure that guarantees a subset that contains the best. Doing that, the subset had 181 systems left, with the same amount of data as used by BYPASS to get to 7. Finally, here are some of the key references for the talk. Again, I'm sorry not to have been there with you, and I'm sure Raghu Pasupathy would be happy to answer any questions.